Do you know how much power the stuff in your life uses? Great. Except that doesn't matter. I'm actually quite serious. Knowing how much power in watts your devices use can be helpful, and it does matter in some circumstances, but it's usually nowhere near as important to your life as how much energy those things use. This may sound like one of those overly pedantic fixations, but it's not. Power and energy are very different concepts. They are closely linked, but that's not the whole story. And unfortunately, the units we use to discuss power and energy can be very confusing if you're not well versed in energy speak. However, if you can wrap your head around precisely how power and energy influence each other, I promise a whole lot of stuff in your life gets much easier to understand. Now, you might think I'm going to start by discussing electricity, but before we get there, I want to instead talk about this. This is a bottle of liquid propane. When sold in this kind of bottle, it's commonly used as a camping fuel. The propane has energy stored in its chemical bonds, and we can release that energy by allowing the propane to leave the bottle, vaporize, and mix with the atmosphere, which creates an air-fuel mixture with a good deal of free oxygen. And when we ignite that mixture, it burns, a chemical reaction known as combustion. The useful byproduct of that combustion is heat, the most basic form of energy. Devices which burn propane in a controlled fashion are how we make use of the propane's stored energy. Devices such as this camping stove. The stove itself is incredibly simple. Other than its overall physical structure, it's little more than a pipe which leads to a pair of valves which then feed nozzles inside these two burner elements. Connect a propane bottle up to that pipe using this very flimsy and precarious pressure-regulating hookup tube thingamajig, and once you've done that, opening those valves will allow some of the propane to leave the tank, after which it goes through the nozzles and ends up in the burners, where it mixes with air. Press this igniter button, which strikes a piezoelectric crystal in order to produce a spark near where the propane-air mixture exits the burners, and whoomp! You've got fire! And now you can cook your delicious whatever. But how much delicious whatever are you able to cook with that bottle of propane? That's a good question, and its answer has to do with energy. Remember, we are burning the propane to release its energy. Since we can only burn it once and then it disappears into the atmosphere, the quantity of propane in the bottle represents the total amount of heat energy that's available to us. When new and full, that bottle contained 1 pound of liquid propane. That's 453 grams. But that's it. When it runs out, it runs out. Now, when it comes to figuring out how much we can do with a bottle of propane, there's what might seem like a complication. If you've used any kind of stove before, you'll know that we don't always use them in the same way every time we cook. Sometimes we might need to boil a big pot of water, but on other occasions, we might need to do gentler kinds of cooking, such as simmering. To address those varying needs, the valves on the stove can release the propane from the bottle at different rates. Watch. As I close the valve down and slow the rate of fuel flow, the flame shrinks and isn't as hot. This lets us do those gentler cooking tasks by introducing a limit to how hot a piece of cookware can possibly get when sitting above the flame. But when I set the valve to its wide open setting, the rate of fuel flow increases, so the hotter and larger the resulting flame is. You can even hear that difference. And just what exactly is that difference? It's power. Through adjusting the rate of fuel flow, the valves adjust the power level of the burners, and thus the size and heat of their resulting flames. Critical to note is that power is not how much propane is in the bottle or even how much we've burned. Instead, power is how quickly we are burning through the propane and releasing its energy at any given moment. Power, therefore, represents an instantaneous energy intensity, which is not the same thing as energy itself. Why is that so important? Well, because energy is what actually accomplishes work. Getting things done, like bringing water to a boil or cooking a piece of chicken, requires a certain amount of energy. You can actually calculate how much energy it takes to bring, say, 6 cups of room temperature water to a boil. That's just a fact of physics. And we also know how much energy the propane contains per gram. So we can work out precisely how much propane we're going to have to burn to boil 6 cups of water. I won't go through that calculation, but it's on your screen now. And if we assume half of the energy released by the stove will actually make it into the water in a pot, a lot of heat from an open flame ends up going around a pot, so there are pretty heavy losses to consider, then we'll find that to produce the necessary heat energy to boil 6 cups of water on this stove, we need to burn about 20 grams of propane. That's roughly 5% of a full bottle. So here's the key question. Does it matter what power level we have the burner set to? Aside from marginal efficiency effects, no it doesn't. 20 grams is 20 grams. That's how much propane we're going to use. How quickly we burn it doesn't matter. And yet, here's where things can start to get confusing. When it comes to how you and I interact with our energy resources, time absolutely matters. In fact, time is the key to understanding what power is and how it relates to energy consumption. Consider that the stove doesn't allow us to burn all of this propane in an instant. If it did, we wouldn't be burning it so much as we'd be exploding it. We don't want that, so the stove limits how quickly the propane can leave the bottle, and thus it limits how quickly we can release its heat energy. The fastest rate at which this stove will let us burn propane on each of these 2 burners is about 3.8 grams per minute. And believe it or not, that right there is a power figure. It's a very weird one, but 3.8 grams of propane per minute does indeed accurately describe this power level. Remember, power at a conceptual level is how quickly we are using energy. And since the propane is our energy resource, a figure which tells us how much we burn over a given period of time describes power. Of course, grams of propane per minute is not a conventional power unit, but let's think about what it can tell us. While it may not be easy to predict how much propane a cooking task will require, since we know we burn through 3.8 grams of propane every minute the burner is set to high, then if we know how long we've been using that burner on high power, we can actually determine how much propane was burned. It's simply a matter of taking that power figure and multiplying it by the total runtime. So, for example, using 1 burner on max power for a total period of 10 minutes will tell us that we used 38 grams of propane, 3.8 grams per minute for 10 minutes. The upshot is that power figures, when runtime is also known, give us enough information to determine how much energy was used. Of course, we don't typically use grams of propane per minute, but the thing is, every power unit is describing the same thing, power, so you can convert between them. This power level is also 4.3 horsepower, or 11,000 BTUs per hour, or not quite 1 ton of refrigeration, or the power unit you're probably most familiar with, 3,200 watts. Yes, in case you weren't aware, the watt is not exclusive to electricity. The watt is power. It can mean electrical power, but it can also mean heat output or mechanical power. Doesn't everybody know 1 horsepower is 746 watts? Of course, we usually reference the watt in the context of electrical devices. So I guess we should transition to talking about electricity. First though, what exactly is the watt? Simple. 1 watt is equivalent to 1 joule per second. Now, Okay, the joule is a unit of energy, but don't worry, you don't actually need to know what exactly the joule is. You just need to know it's a specific quantity of energy. And how many joules of energy get used in 1 second is watts. It's that simple. Note to physicists, I am aware of the conservation of energy and that saying joules which get used is not technically correct, but this video is to help people understand how they use energy resources, so please just roll with it. Now, since watts represent the number of joules used per second, then just like in the stove example, if you know how many watts a device needs to function and you have a record of how long the device has been functioning, you will be able to determine precisely how many joules, and thus how much energy, that device actually used during that time. However, joules are teeny tiny little bits of energy. A 10-watt light bulb consumes 600 joules every minute. Now, the good news is, just as power is power, energy is energy. There are many different units we can use to quantify energy, but they all describe the same thing, so we can convert between them. When we are talking about electrical energy, because the joule is really tiny and most people don't have much feel for what a joule is anyway, we usually use a unit of energy called the watt-hour. Watt-hours are what they sound like. It is simply power in watts multiplied by the total runtime in hours. The result you get is watt-hours. So, for example, that same 10-watt light bulb, after running for 3 hours, will consume 30 watt-hours of energy. 10 watts times 3 hours equals 30 watt-hours. Quite simple. And just for funsies, since there are 3,600 seconds in an hour, that means there are 3,600 joules in a watt-hour. So 30 watt-hours is equal to 108,000 joules. Perhaps you see why we don't usually use joules. But unfortunately, although the watt-hour is a very simple concept and it's very simple to calculate, it can be a little confusing if you're not used to it. Watt-hours sounds dangerously close to watts per hour, and that might land in your brain as a speed at which we use watts. But the thing you've got to keep in mind about the watt is that the watt itself is a rate. It's literally joules per second, after all. So in a sense, the watt is a speed of energy. To actually quantify an amount of energy from the watt, we need to know how long we've been running at that speed. The hour in watt-hour allows us to determine the product of a known rate in watts and an hour's time. This means the watt-hour is both a calculation that derives energy from power and time and the result of that calculation. That's, I think, what makes it confusing if you're not well versed in energy speak. Not only can it seem pretty clunky to quantify energy as a calculation, but the terminology watt and watt-hour is linguistically backwards compared to how we typically describe rates and quantities. Usually, when we see a time component in a unit, like miles per hour or revolutions per minute, we are describing a rate by saying what will get done in that time period. But because the watt itself is a rate, joules per second, it stands on its own. Much like a speed reading can't tell you a distance traveled without knowing how long you've been traveling at that speed, the watt can't describe a quantity of energy unless we add the total time to the mix. And that's the point of the watt-hour. And although it can seem clunky, the watt-hour is incredibly useful to understanding energy because it brings the time part of this whole deal front and center. For instance, say you've got a television which uses 150 watts of power. If you want to know how much energy it uses, you need to know how long you've been watching TV. After you've been watching for 2 hours, your TV will have consumed 300 watt-hours of energy. It's simply the 150 watts the TV uses when it's on, multiplied by the runtime of 2 hours. Watt-hours. Pretty simple. When we are dealing with time intervals smaller than an hour, you multiply by the fractional hour. For instance, to calculate the energy used by the same TV in 15 minutes, a quarter of an hour, simply multiply 150 watts by 1/4 of an hour, or 0.25 hours, and that gives us 37.5 watt-hours. It's a simple calculation, and hopefully you see how it works kind of like a tally system, which adds to the energy total the longer your devices draw power. Since we've all got a lot of devices that need more than 1 watt of power, in practice we usually use the kilowatt hour, which is simply 1,000 watt-hours. Just makes the numbers smaller. And if you were to look at your electricity bill, you will find that you were billed for the total number of kilowatt-hours you consumed during that billing period. And remember, I'm going to be a bit obnoxious about this. That means you were billed for the total amount of energy you consumed. Whenever you see the word hour after the word watt, or in an abbreviation the letter H after the letter W, then you are looking at a quantity of energy, not a power figure. And when it comes to your energy bills, energy is the only thing that matters. For electricity bills, there is an asterisk there which I'll get back to, but most residential electric bills are not impacted by the power draw of your home. They are only impacted by your home's total energy use in kilowatt-hours. This is crucial to understand, because if you're not in an energy-first mindset, it's easy for power figures to mislead you. For instance, something that I've run across again and again pretty much every time I've talked about electric cooktops, induction or conventional, is this idea that electric cooking is wildly expensive compared to gas cooking. Now, there is some logic to why people say that. In general, methane gas is a less expensive source of heat than electricity is. And electric cooktops do indeed need to be hooked up to beefy 40 or 50 amp circuits because they can draw a lot of power. If all the burners on my stove at home are set to high, the stove draws 8,500 watts. That's a scary big number and is indeed quite a lot of power. But power isn't what matters to your energy bill. Energy is. And the thing about household cooktops and ovens is that when it comes to a typical home's energy use, they're practically rounding errors. Think for a moment about what cooking is. It's simply heating food. And yes, sometimes it makes things very hot, but you're only making small things very hot. That heat, even though it is often intense, is very concentrated, and this ultimately means it's not actually a large amount of energy. Now remember that whole time thing? Unless you're running a restaurant out of your home, you only use your stove for a couple hours a day, likely less if you're not an adventurous cook. But if your home is climate controlled, then you've got a machine which is running 24/7 to maintain the temperature of a much larger object than tonight's dinner. To give you some actual numbers, my home's air conditioner is a little 2-ton unit, which only draws about 2 kilowatts, that's 2,000 watts, when it's running. But during the height of summer, that thing will run for somewhere between 6 and 12 hours each day. Taking a low average of 8, this means my air conditioner is responsible for about 16 kilowatt hours of energy use per day. How does that compare to my stove? Well, to give you a specific example of how much energy an actual cooking task needs, sometimes I scramble 3 eggs in a small pan like this. And when I do it, I use one of my stove's small 1200 watt burners. It takes the stove maybe 2 minutes to preheat the pan enough to melt a pat of butter in there, and once I put the eggs in and start scrambling, they're usually done within 5 or 6 minutes. Now typically I reduce the power level of the burner once they're starting to firm up, but to make the math easier, we'll just pretend that I run the burner on full power for the entire 8 minutes. So, how much energy does that use? Well, that's 1200 watts, or 1.2 kilowatts, multiplied by 8/60ths of an hour, which results in 0.16 kilowatt hours of energy. That is nothing! Literally just 1% of what my air conditioner uses in a day. And as far as how much that energy costs, even with a horrendous electric rate of 50 cents per kilowatt hour, it would only cost about 8 cents to scramble those eggs. With my electric rate, which averages around 10 cents per kilowatt hour, it doesn't even cost the 2 cents an opinion is worth. Quick note, I calculated these numbers based on my guess of how long it typically takes to scramble eggs with my stove, and I overestimated by a lot. I like my eggs very dry, and despite that, the total time spent including heating the cold pan was only 5 minutes 15 seconds. I also turned the burner down to half power at the 2-minute 45 mark, meaning that the actual energy expenditure here was approximately 0.08 kilowatt hours, or 80 watt hours. It's a tiny amount of energy. Just the lava lamps in my set used more energy in the time it took to shoot this video. Now, granted, scrambling 3 eggs is not much of a cooking task. But even the most energy-intensive cooking tasks, like boiling huge quantities of water, don't require that much energy in the context of a home. Assuming a 25% loss, it takes about 2 kilowatt hours to bring 4 gallons of water to boil on an electric stove. So even if you do that every day, the 60 kilowatt hours that would require over a month would only represent about 6.5% of the average US household's monthly electricity consumption. People who fixate on the cost to use an electric stove frankly just don't understand energy. Or they're peddling culture war nonsense. Now, to be clear, I'm not trying to sing the virtues of electric cooking. What I'm really hoping to help you understand here is the importance of having an energy-focused mindset. Power figures in watts rarely matter. Energy does. And if you put energy front and center in your mind, not only will it help you understand your electric bill, but it can bring you a more specific understanding of precisely why the machines in your life cost what they cost to operate. I really want to encourage you to spend some time thinking about this. Energy doesn't have to be a mystery. And if you can develop an intuition for it, then you'll have a much better grasp of the opportunities available to you with the infrastructure in your home, and the challenges too. And it's time to drop the truth bomb. There is in fact just one single most important factor to determining how much energy you use, and it's almost comically simple. It's what you do. It's not actually complicated. It's the stuff you do in a day that determines how much energy you use. Every time you ask a machine to complete a task for you, it takes a certain amount of energy. And if you don't have any idea how much energy certain tasks require, you can figure that out. One option is to use a plug-in energy monitor like this, which will not only give you a reading of how many watts a device is currently drawing, but will also tell you a cumulative energy consumption in kilowatt hours. And once you have that answer, now you know. It's always going to take the same amount of energy to do the same thing. If you don't have one of these things handy, you can use the power rating of the machines you're using, which they usually list somewhere on them, and how long you need to use them to complete the task in order to give you some idea. But you have to be careful with that. Power labels and runtime don't always provide the best answer, since many devices don't consume a consistent amount of power. I mean, sure, my stove has a label on it which tells me its maximum power draw, but its actual power draw depends on what burners I'm using and the power levels those individual burners are set to. The area where power labels can trip you up the most is when you're looking at a machine which is always in use. A refrigerator, for instance, will tell you its maximum current draw in amps, which you can multiply by the incoming voltage to determine watts, but your refrigerator isn't always running. Plus, if your refrigerator has automatic defrosting, its max power input is for the defrost heaters, which require much more power than the refrigeration compressor does. Now, the good news is, you can look up your refrigerator's model number and find an energy guide label for it, which will tell you how much energy that model typically uses over a year. And this is true for some other appliances as well. But those figures are determined through testing, which assumes an average usage pattern and an average operating environment, which is not always reflective of your particular reality. That is a complication for sure, but it doesn't have to feel like one. If you can get your brain in the groove of first thinking about what is actually getting accomplished, it can be very clarifying. Let's go through another example of a device which needs a lot of power to function, yet doesn't necessarily have a huge impact on your energy bills. Electric clothes dryers here in the US often have heating elements which run at 4,500 watts. Again, a scary big number, and if you've ever looked at the chonky power cord your dryer is hooked up with, you might assume the dryer has a huge impact on your energy bill. Now, it can, and I don't want to minimize that, but if you've got your own clothes dryer at home, well, think about it for a minute. Even with a big and growing family, most of the time the dryer just sits there doing nothing at all. It doesn't require any power, and thus it doesn't consume any energy, unless you're actually using it. It's hopefully pretty obvious that how often you use a dryer is going to impact how much it costs to use, but what's perhaps less obvious is that the most precise indicator of what your dryer's impact on your energy bill will be is not how often you use it or even how long it runs. It is in fact the total amount and wetness of the laundry you're drying with it. Drying clothes is the work you're asking it to accomplish, and the total amount of work you throw at it will determine how long the dryer actually needs to run its heating element during the dry cycle. See, the heating element doesn't actually run constantly during a dry cycle. It turns on and off to maintain a specific temperature, and most dryers have different temperature settings, helpful for drying more delicate items. These factors mean its average power draw isn't consistent load to load. But since the task of the dryer is simply to get water in clothing to evaporate more quickly, the more water in those clothes, the more heat energy the dryer has to add to the tumbly thing before they're dry. So again, it's what you do that matters, not the power draw of your devices. And that goes for nearly everything in your life, regardless of its energy source. There are some things you're not necessarily in much control of. You can't control the weather, for example, so how much energy is necessary to keep your home warm or cool varies from day to day. But the indoor temperature you choose to maintain will impact how much energy is required. And for the devices in your life which don't run unless you're using them, the work you ask them to do is the main factor to how much energy those devices need. How much food are you cooking? How many hot showers do you take? How much laundry are you doing? Heck, even a car uses energy based on how much you actually drive it. So the answer to how much gas am I buying is pegged mainly to how far you actually drive your car every day. My sincere goal with this video is to stress the importance of an energy-first mindset. And by now, I hope you see how energy matters much more than power. However, power levels do matter on some occasions. What are those? Well, there are basically three ways power can become significant. The first is the one we've been dancing with this whole time. Time. More powerful devices can accomplish their work more quickly. For instance, a 600-watt microwave oven will take twice as long to pop a bag of popcorn as a 1200-watt microwave oven. They will both use a similar amount of energy to complete that task, but because the 1200-watt microwave can pump energy into the popcorn more quickly, it will finish the job in roughly half the time. Similarly, the 3-kilowatt kettles they've got in the UK can boil water in half the time that our 1500-watt kettles over here can. But energy is energy and water is water, so the only difference between them is the speed at which they finish the job. They both use the same amount of energy to do it. Power levels become especially important to speediness when what we are doing requires larger quantities of energy. For instance, I have an electric car. It's a Hyundai, and it's got a 77.4 kilowatt-hour battery pack. Now, you heard hour after watt, So that figure is telling us how much energy the battery pack can store. And that's a good deal of energy. And do you see how power is going to impact how long it takes to refill that battery? My home charger can deliver 7.5 kilowatts of power. So, pop quiz. How many kilowatt hours can my 7.5 kilowatt charger supply to the car every hour? 7.5. It's not a hard one. So, how many hours does it take to charge my car with my 7.5 kilowatt charger? That's easy. Divide the 77.4 kilowatt hours of energy the battery can store by the 7.5 kilowatts of power my charger can deliver, and we get 10.32 hours of time. But that would be a completely empty to full charging time, which I've never actually needed to do. I've also ignored efficiency, but I've been doing that this entire video. We'll touch on that at the end. The reason electric car nerds are obsessed with the power numbers DC fast chargers can put out is precisely because the more powerful they are, the more quickly they deliver energy, which means they shorten the time it takes to recharge a battery pack. I don't want to get too fixated on this because there are many factors at play here between individual car models and specific charging equipment. But the reason my car can charge from 10% to 80% in 18 minutes when it's on a sufficiently powerful charger is because its battery pack can accept an average power input of about 170 kilowatts in such a charging session. That is a bonkers amount of power, which requires a significant grid hookup at a DC fast charging site. But it's not actually a huge amount of energy. It's only about 52 kilowatt hours. My charger at home, since it's power limited, needs roughly 7 hours to deliver the same amount of energy, taking the car from 10% to 80%. But it's still the same amount of energy. More power just speeds up charging, which is important on a road trip or if you need a quick charge, but it doesn't change how much energy a car needs to drive a certain distance. Moving on from charging big batteries, the second way power can matter is much more significant, and that is when we have a power limit. You've heard me talk about electric service levels before. They're usually described in terms of amps for reasons having to do with how much current you can safely send through a wire, but an amperage limit is also a power limit. I have 100 amp service in my home, which means that the most power my home can draw before the main breaker is at risk of tripping is about 20 kilowatts. The main thing that limit means is that I can only do so much stuff at the same time. However, since there are only 24 hours in a day, a power limit is ultimately also an energy limit. With 100 amp service, I can only consume 480 kilowatt hours of energy every day. But, I barely use more than that in the average month, so the only practical limitation it presents to me is how many devices I can have operating at the same time. That is, unless my home actually required so much energy that 20 kilowatts of power couldn't fulfill its needs. I know that's never going to happen for me because I live in a townhome, but if I had a grotesque McMansion which was heated by electricity, then on the coldest winter nights we face in Chicagoland, 20 kilowatts might not be enough power to keep the house warm. Big houses have bigger heat losses, and the colder it is outside, the faster they lose heat. So if a big house is losing heat faster than 20 kilowatts of power can replace it, the house won't stay warm. And even if 20 kilowatts was just enough to maintain a toasty warm temp inside when it's minus 15 outside, well, you need some overhead for other things like lights, appliances, and whatnot, which is why those larger homes have larger electrical services. Quick note, what we just talked about is why it's important to know your home's actual heating and cooling needs. I made a video about HVAC system sizing, and really what size means in the context of HVAC systems is power output. Heating a home is really just an exercise in replacing the heat energy that leaked out of it through walls and windows. And the rate at which that energy leaves is a power figure, and therefore it tells you how much power you need to replace that heat. Through testing, I determined my home only needs a sustained 5 kilowatts of power to maintain 69 degrees Fahrenheit inside when it's -10 outside. That's why I'm confident my home won't ever need a service upgrade. My power limit of 20 kilowatts still leaves plenty of overhead. I'll link that video if you want to know how that testing happened, but long story short, my home needs significantly less heat energy than the size of my furnace would suggest. But even within an individual dwelling, power limits sometimes get in the way. You don't just have the service level limitation of your entire home, you can only draw so much power from each individual electrical circuit inside your home. Here in the US, this is generally going to be either 1800 watts or 2400 watts, depending on the circuit. And that puts a limit on what precisely you can do in each area of your home. Usually, these power limits don't matter all that much outside of the kitchen, and if your home was built in the last 50 years or so, you probably have at least 2 circuits in the kitchen anyway. But if you've ever had a circuit breaker trip on you when running a portable air conditioner or heater, then you'll have discovered firsthand the significance of a power limit. Go over it for too long, and the circuit breaker will trip to keep your house from burning down due to overheating electrical wires. So, it's a good thing that there are circuit breakers, but they're a limit. To be clear though, power limits in general only affect how much you can do at the same time and/or how quickly you can do any particular thing. They only become limitations on what you can do if you actually need more energy than a power-limited circuit can provide. And since over 24 hours, even a standard 15-amp receptacle can deliver 36 kilowatt-hours of energy, that's generally quite a rare occurrence in a typical household environment. And if you are running into that issue a lot, what you've got is either a design flaw in your home or you have atypical needs. Okay, so the third way power levels can matter, and this is specific to electricity, has to do with demand charges. Electric meters used to be fully analog spinning things which could only log kilowatt hours, and a meter reader, a human person, would swing by your house each month, actually look at it, and then write down the numbers on the display. But these days, those are rare. Electric meters of today are electronic devices which can log minute-by-minute usage and report that usage to the utility through a wireless mesh communications network. And certain utilities may assess a charge based on the maximum power draw in kilowatts of your home at a particular time. They do this because managing the electric grid is very difficult, and the more power is being used at once, the harder all the generators on the grid have to work to supply that power. So fee structures sometimes exist in an attempt to get electricity customers to lower their power draw during periods of high demand. However, demand charges are entirely dependent on where you live, your utility company, and your utility company's policies. Here in the US, demand charges are rare in residential service. You're usually only billed by the kilowatt hour. Many utilities allow people to opt in to certain schemes, for instance giving folks a bill credit if they lower their power demand when the utility requests them to, but mandatory demand charges are pretty rare on the residential side. Commercial customers, on the other hand, they often are assessed a mandatory demand charge. For instance, here at the office, my electric bill comes with a fun $11 per kilowatt fee, determined by the highest power draw my meter saw during the midday on-peak period each month. It's great. I love it. But if you are subject to demand charges, you should find out exactly how they are assessed. It's unlikely that, say, using the microwave for 2 minutes is going to kick off a demand charge. What's more likely is that the utility looks at a moving window of 15, maybe 20 minutes, and your demand charges, if you have them, are calculated by the average power draw during that window. But I don't know what your situation is, I'm just encouraging you to look into it. A bunch of Europeans have mentioned that their bills include them, but in the land where kettles run at 2,000 or 3,000 watts, I don't think they're quite as granular as some folks seem to think they are. And on a closing note, it's time to talk about efficiency. It is true that the same device will always require essentially the same amount of energy to complete a given task. But a different device may be able to do the same task while using less energy. That's the gist of energy efficiency. We want to waste as little energy as possible, and we've made great strides to that end by designing devices which produce more useful work with the same amount of energy. Undoubtedly, the largest leap we've made in efficiency comes from the humble light bulb. When I was a kid, incandescent light bulbs were still the norm, and this meant most light bulbs used 40 or 60 watts, with plenty using more than that. Each individual light bulb didn't need all that much power, but you'd usually have at least a few burning at the same time, and that quickly added up. Thinking back to my childhood kitchen, that room alone had 4 60-watt light bulbs. And this meant the lights used the same amount of energy in just 20 minutes as it took to scramble my eggs. These days, though, lighting technology has advanced to the point that modern light bulbs need as little as 1/10 as much electricity to produce the same amount of light. This is fantastic and has meant lighting is no longer that significant to energy bills. And since modern light bulbs don't produce nearly as much waste heat, they've also reduced the energy required for cooling. However, in other areas, there isn't actually much more efficiency to be found. When we are dealing with electricity, things are a little weird. Some things electricity does are perfectly efficient. This is the case for electric resistive heat. Every single watt-hour a heating element consumes is released into its environment as heat. So for example, when I use my stove, the only heat losses are the result of imperfect heat transfer between the heating elements and the cookware. But electricity generation is not 100% efficient. Only some of the thermal energy in a fuel being burned in a power plant is successfully captured by a generator and converted to electrical energy. Of course, that's not something you have control of, but it's one reason we are working to make electricity generation more efficient. Luckily, I don't know if you've heard this, we discovered this technology where you can build a device one time, stick it in a field, and then it collects energy from the sun or wind for free. What a concept! Free and sitting in a field sounds much easier than constantly having to pay people to search for fossil fuels, extract them, purify them, and finally move them across the country just so we can feed the result of all that hard work to a generator where the fuel gets burned up and disappears into the atmosphere, meaning we have to keep doing it forever or the generator will stop and no more electricity. I honestly don't know why I have to explain that while yes, it does take effort to manufacture solar panels and wind turbines and batteries, you only do that one time and then you get decades of free energy from them with no input. It's cost-effective at this point for people to buy their own oversized solar arrays and batteries and live off-grid. So why the hell are you letting people convince you that renewable energy is impossibly difficult and expensive? Sorry, got a little off track there. But you should look into what we actually do with all the corn we grow in this country. 40% of it isn't food feeding you or even livestock. It's for feeding cars. We're doing real great. Anyway, there aren't many efficiency gains to be had from appliances in the kitchen, but the big energy draws of your home, mainly your HVAC system and your water heater, are important areas of focus. With heat pumps, my very favorite things, we can move heat energy from one place to another, and it turns out we can move more heat with a heat pump than it takes to run the heat pump. Really efficient heat pumps can turn 1 watt of input power into 4 or 5 watts of heating power, depending on conditions. And that's no glitch in the matrix. It's the power of moving heat energy rather than creating it. And that's no glitch in the matrix. Now, I could talk about heat pumps all day, but I will just say my trademark phrase for those who may not be aware of it. Air conditioners are heat pumps. This means if you have an air conditioner, congratulations, you've got a heat pump, and that thing works by collecting heat energy from inside your home and pumping it outside. The only thing that turns an air conditioner into a heat pump is a component called the reversing valve, which allows that air conditioner to run in reverse, collecting heat from outside and moving it inside. And that means the same machine can provide heating and cooling. I say this with animated frustration because heat pumps are touted as new technology, when in fact, it's very old technology, and the only new development is that they've become good enough to work effectively in cold climates like mine. Yet, many HVAC professionals refuse to read the memo. Then of course there's heat pump water heaters and heat pump clothes dryers, which are also extremely thermally moving. But I'll move on to a little thing we call vampire drain. Many electronic devices are never truly off and instead operate at very low standby power levels. Honestly though, we've made great strides in this area lately, so it's not worth too much consideration these days. But on the other hand, we also have a habit of sticking gadgets like smart speakers and cameras around the house, which aren't huge power draws, but they add up. I'll ignore those though. Instead, I want to talk about something which is very funny when you do the math. My microwave, as do many, has a clock. And to show you the time, it uses 0.7 watts. That means it consumes 16.8 watt-hours per day just being a clock. Now, it uses 1,650 watts when it's heating stuff, but microwaves are famously quite fast at that. And that means, depending on how I use my microwave, its clock can actually use more energy than microwaving things. I need to use the microwave at least 36.6 seconds every day to heat food just to break even with its clock. And I don't use my microwave every day. Now, I'm pretty sure on net the clock is less significant since when I do use the microwave, I'm often using it for several minutes. But there have absolutely been days when all I did was melt some butter, meaning the clock used more energy. This is not only funny, but should also make you realize microwave ovens are an extremely energy-efficient way to heat food. You only use them for a few minutes at a time because they're literally bombarding food with radiation and directly heating it. It's induction cooking on steroids. Yet, people often seem ashamed of using microwave ovens. I think they're pretty freaking neat. But anywho, it's time to wrap up. Energy doesn't have to be a mysterious thing. Yes, there's a lot of complexity to how we obtain energy sources these days, and I really hope people will step outside the familiar and embrace the possibilities of energy resources which don't just disappear after you use them once, like all the propane in this bottle will, or all the gasoline you've ever put in a car's gas tank. Sorry. But see, that's really the whole reason I'd like us to be thinking about energy a little more. When we have access to functionally limitless amounts of energy, like electricity coming from a power grid, how much we use is really easy to ignore. It's not going to run out like the propane in this bottle will. All we have to worry about is the number on a bill. But that doesn't mean we shouldn't be wise about it. As I hope to have helped you see, an intuitive grasp of power and energy is really helpful. It allows you to cut through all the noise out there. Like, for instance, when someone says using an electric space heater can save you money on your heating bills. Sure, it might, but most of the time you hear that, it's just a sales pitch. You need to turn the temperature way down in the rest of your home in order to offset the added cost of using a space heater. And every single time you run across some miracle energy-saving doodad, it's a scam. There isn't one weird trick to lowering your energy bills. Energy is energy. Your bills are based on what you do. So if you want to lower them, you have to make different choices. And when you know how power relates to energy, You have the knowledge you need to make those choices, to know what choices actually matter and why, and to know what choices are possible. This is all just a numbers game. Dust off those algebra skills and start running some theoretical scenarios in your mind. Thinking of getting one of those portable power banks in case of a power outage? Well, you need to know how much power it can actually put out to determine what devices it can possibly run. And assuming it meets that need, then you need to know how much energy its battery pack can store to get a sense of what all it can do for you on one charge. And finally, if you know how much energy, say, your refrigerator actually uses in a day, you'll know how long that battery bank can keep it going. I think it's fair to say that that sort of understanding is going to become increasingly necessary as time goes on, or at the very least, increasingly useful. We're coming up with all sorts of ways to both harvest and store energy these days. And the numbers you see which describe these machines and techniques aren't just for stats nerds. They mean real things and have real implications to your life. I, for one, think it's really fun to put those numbers in my personal context. And maybe it won't be fun for you, but I think with the right mindset, you'll discover you're solving some mysteries before they even appear. And that, my friends, is powerful. Time to get rid of you. Which side should I take off first? Probably this one. That was cute. Oh, it smells awful. You'll know how long that battery You'll know how long that battery I said it again. Then you'll know how long that battery discovered this technology where you can build a device one time, stick it in a field somewhere. I don't know how there's a loud car right now when I started talking about that. You will be able to determine precisely how many... Well, fine.